Good afternoon, everybody. Welcome back. I hope that you had a nice 4-day break from everything and you were able to have an enjoyable Easter weekend with your family. We're going to be moving on today and just continuing with the same type of problems that we were working on last time, max-min problems or optimization problems. We're going to be doing this today and tomorrow and I believe Friday as well. Today's example problems will be simpler than the ones that we dealt with last time because we won't need an equation of constraint. An equation of constraint, don't forget, is an equation that you use to eliminate extra variables, I guess is one way I could put it. So if you're trying to maximize a quantity and you have that quantity defined in terms of more than one variable, then you need to eliminate those extra variables and you use an equation of constraint to do so. We'll discover with the two examples we look at today that we won't need an equation of constraint because we'll end up with a function that defines what we want to optimize in terms of only one variable right out of the gate. We won't have an extra variable. And the two problems we're looking at today are actually ones that should be familiar with you. The first one is a problem that you dealt with in Math 30-1. I designed a lesson in 30-1 centered around this in polynomial functions in that polynomials unit because I'm trying to prepare you for this application in calculus. You start off with a 74 centimeter by 30 centimeter piece of cardboard and we're going to make what's called an open box. This is done by cutting 4 equal sized squares from the corners of the cardboard and folding up the sides. And if this were in class, then I have these things already built and I would show you different designs, but we're not there, so you'll have to use your imagination just to help you visualize what's going on here. These two lines that I'm indicating, once the box is constructed, become the edges that I'm indicating here. On the other hand, these two lengths on the flat piece of cardboard, when the box is constructed, become these two edges. And finally, the height is going to be a result of these lengths joining each other when the sides are folded up. So you can see by looking at the diagram where we're going to get the length, width, and height from. The first thing we're going to have to do is come up with a function for the thing that we want to, in this case, maximize. Well, you're trying to maximize the volume of the box, which means we need to come up with an equation for volume of a box. Well, that's pretty easy. A volume of a rectangular prism is length times width times height. And now we need to define those three variables in terms of x, because the question is what length x should be cut to maximize the volume. Well, if we take a look at the diagram, we already know that x is the height. X is the actual size of the square, the length of the edge of the square that's cut out. So when I fold it up, each of these heights is going to be x. When I talk about the length of the box is the length of that yellow line. That yellow line can be found by taking 74 centimeters and subtracting off the x above it and the x below it. That 74 is this entire distance, but this distance is x and this distance is x. So the yellow line would be 74 minus 2x. The same argument can be made for the width of the box, the bluish colored line, that it would be 30 minus 2x. So in the end, we come up with the following formula for volume. The length is 74 minus 2x. The width is 30 minus 2x. And the height is x. And then I guess all that remains to be done here is to find dv dx so that we could find our critical values for x. But probably what you want to do is multiply out these three factors to get a degree 3 polynomial. I don't think you want to differentiate the function as it stands right now. So it's looking like I'm going to need a calculator here. I'm going to FOIL out, first of all, the two binomials, then we'll worry about multiplying by that x. But I don't trust myself to multiply out those numbers without a calculator. 30 times 74, I think I know what it is, but 2220, yep, that's exactly what I thought. So we get 2,220. My outer would be minus 148x. My inner would be minus 60x. My last is plus 4x squared. And of course, I have to multiply that by x. I'll double check my numerical math here. 2 times 30 is 60. 2 times 74 is 148. Looks good. So volume will be equal to 4x cubed. I'm multiplying everything by x, and I'm also taking the liberty of writing it in descending order of degree. Then I have minus 208x for my outer and inner, but I'm multiplying by x, so that's minus 208x squared. And then I have plus 2,220x. Here's a little tip for you. I've seen a lot of students now solve that equation to find their critical values of x. They set that expression rather equal to 0 and they solve it to find the critical values of x. And it's very common for you to miss the most important step here, which is to differentiate it. We don't care when that equals 0. We don't care when the volume is 0. We care when the derivative is 0. So we still have to find dv dx, 12x squared minus 416x plus 2,220. Just double check. 4 times 3 is 12. 2 times 208 is 416. The derivative looks fine. It would be nice if this factors to give us our critical value of x. I'm pretty sure it doesn't, but I believe 4 is a common factor. So I can take a 4 out and get 3x squared minus 104x plus, I want to say 555, but I better find out. $555, and I'll just check 416. I shouldn't have to do this, but just wanted to double check. So plus 555. And now, as I said, what you would like to do is factor that, if at all possible. I don't think it's factorable, but we can do the b squared minus 4ac test. And remember, if b squared minus 4ac is a perfect square, then the quadratic is factorable. B squared is negative 104. If you're going to actually put the negative in and square that with the negative, make sure that you put it in brackets. Minus 4 times 3 times 555 gives me, I must have typed something wrong there. Oh, I didn't need the bracket. 4156. So b squared minus 4ac is 4,156. I'm pretty sure that's not a perfect square. It's not a perfect square, so this remaining piece that's quadratic in the brackets after we took the 4 out is not factorable, which means that we need to use the quadratic formula. X is going to be equal to negative b. X is equal to negative b plus or minus root b squared minus 4ac, which we already have calculated. It's 4156 all over 2a. which means x is equal to negative b, which will be positive 104. B is negative 104, plus or minus the square root of 4156 all over 2a, and a was 3, which means it's over 6. Now, you know what? The square root of 4156 is simplifiable. I can see that 4 divides into it, so you can break it up into root 4, root whatever else, and write it as 2 root whatever else, and then you can start canceling a 2 out of the top and the bottom. But I don't care about that. That's grade 11 math. I'm interested in the calculus here. So what are our 2 critical values of x? One of the critical values of x is 104 plus the square root of 4,156 divided by 6. And the other critical value of x is 104 minus the square root of 4156 all over 6. And I told you last time that for the time being anyway, there's no reason for us to have to do a first derivative chart. No matter how many critical numbers you get, only one of them will be valid. So in order for us to see which one of these is usable and which one is not, in other words, which one is in the domain and which one is not, we should calculate approximately what these are so we can talk about the actual number. It's going to be an approximation in decimal form. Okay, we have 104 plus the square root of 4156. And then we have to divide that whole deal by 6. So we get approximately 28.1 centimeters. And then for our other critical number, we're going to have 104 minus the square root of 4156, then divided by 6, which gives me 6.6 centimeters, approximately. And 6.6 centimeters is going to be the answer. The length of the side that we're going to have to cut out will be 6.6. Now, I'm not going to leave it just hanging there without an explanation. The reason why we're going to throw that 28.1 centimeters over the board, we're going to toss that one out, is because it's not in the domain of allowable values of x. If you take a look at the actual construction of the box, the width of the piece of cardboard is 30 centimeters. And if you are going to remove 28.1 centimeters from each end of that 30, you're going to have nothing left. In other words, there is a domain in this question for x. And the domain is that x must be between 15 and 0. You have to cut out something bigger than 0, but you can't even reach 15. Because if you remove 15 from each side, you're left with nothing on the short side of the box. So that's the answer to the question. And again, I'm not really too concerned about simplifying 104 minus root 4156 all over 6. You can simplify that if you want. I'm interested in the answer. It's about 6.6 centimeters. Let's take a look at the next question now. This is something that you have done, well, you've done a problem very similar to it in Math 20, dealing with revenue. This is not revenue, it's numbers of oranges. So what you have is an orange grove, and for every acre, when they have 60 trees planted on that acre, they get an average of 500 oranges per tree. Which means on that acre, if we were to multiply 60 trees by 500 oranges per tree, on that acre, they get 30,000 oranges in a growing season. What they've discovered is they can plant more trees per acre, but when you plant one additional tree, you get 5 fewer oranges on average in the growing season. Now, why should that be? Well, when you plant more trees, all of those trees are now going to have to share the same nutrients and resources that were in that 1 acre, so each tree gets a little bit less. The question is, how many trees should be planted to maximize the yield? Well, the number of oranges, I'm going to use n as the number of oranges, needs to be maximized. And the number of oranges would be equal to the number of trees per acre Well, you know what? The whole thing is per acre. I don't know that we need to put per acre. On that 1 acre, the number of oranges will be how many trees multiplied by the number of oranges per tree. Well, we need to define another variable here, and I'm going to use x, and x is going to be the number of additional trees. And that means that the number of oranges would be the number of trees, which is 60 plus x, multiplied by the number of oranges per tree, which would be 500 minus 5x. Every time we add 1 tree, we lose 5 oranges. So the minus 5x is minus 5 times the number of trees, which is the number of oranges you lose. Very basic problem from here on out. If this were Math 20, what you would do is FOIL that out and then complete the square to find the coordinates of the vertex. At this level, all we have to do is find the coordinates of the vertex by finding the coordinates of the maximum, which is found by looking at the first derivative. In fact, when I teach this in Math 20, I wish I could just show them that if you knew how to differentiate it, you could get the answer very quickly. Anyway, let's simplify this first. Number of oranges would be, I'll FOIL it out, 60 times 500 is 30,000. My outer is negative 5x times 60, which is negative 300x. My inner is 500 times x, which is 500x. And my last is negative 5x times x, which is negative 5x squared. I'm just going to take a breather here and make sure that I multiplied that all out correctly, and it looks fine. The number of oranges per acre then is going to be negative 5x squared plus 200x plus 30,000. D number of oranges dx would be negative 10x plus 200. And in order for us to see critical values, we should take that derivative and factor it. I'm going to take a negative 10 out and be left with x minus 20. I can see that the only critical value for x here is 20, which means the answer to the question is they need to plant 20 additional trees. Now, I don't know, you can go back and look at the question. If the question said how many additional trees should they plant, the answer would be 20. If the question said how many trees should they plant per acre, then the answer would be 80 because they already have 60. It depends on how the question is worded. So a couple more examples that we looked at today, fairly short lesson. And you don't really have a lot to work on for next time. I am moving on tomorrow, so tomorrow we're moving on to more complicated problems. On page 195, do number 5b, number 6b, and number 7. So just 3 questions to work on for next time. Oh, sorry, and page 188, number 6. So you got 4 questions to get some practice with. Have a great rest of the day, and we will talk to you later.